Today, we are going to discuss on covariant derivative of contravariant vector and covariant derivative of covariant vector. Before starting the discussion on covariant derivative of contravariant vector and covariant vector, we will have some concept of covariant derivative of a vector. So, covariant derivative of a vector vector. Actually, covariant derivative of a vector in a curved space is the coordinate derivative of a vector plus change in vector caused by the change in basis vector. That is, we can write this is equal to coordinate derivative vector plus change in vector is caused by the change in basis. So coordinate derivative of a vector has two terms. Coordinate derivative of a vector and change in vector is caused by the change in basis. Here, this coordinate derivative is also called directional derivative. This directional derivative or coordinate derivative depends on the coordinates of the system. In which system we are doing coordinates of the system. So this is about the coordinate derivative of the vector. Coordinate derivative is different from the covariant derivative is different from the coordinate derivative or directional derivative. Now we will see the covariant derivative of contravariant vector. So for this, let me write first. Vector. To discuss on covariant derivative of contravariant vector, we will start from the transformation equation of the component of contravariant vector. Here V prime I is the transformation equation, is the component of contravariant vector, and its transformation equation is okay. Now, this transformation equation can be expressed in terms of generalized coordinate. For this, we consider x prime I is simply xi and xk is qk, that is generalized coordinate. Then the transformation equation becomes vk. When this transformation equation is differentiated with respect to qj, we have here we can see the first term in the right hand side of the equation, this del xi over del qk, this is actually covariant basis vector. Covariant basis vector, it is epsilon k. When we write the covariant basis vector, this equation in terms of covariant basis vector, we can express this equation in a single vector equation. This single vector equation is instead of writing component, we'll write just vector. We would like to express in a single vector equation. VK. This is a single vector equation. Here, this vector equation is expressed in terms of covariant basis vector. Here is a term differentiation of covariant basis vector with respect to Qj. This differentiation can be expressed in terms of basis vector is here we have introduced a new term. This is a new term. Here we have introduced. This term is called, this is Christoffel symbol of second kind. Symbol, this is Christoffel symbol of second kind. More about this Christoffel symbol we'll discuss in the next class. But anyway, we have introduced this Christoffel symbol, gamma mu jk. Now, we can write this equation once again. We'll have, this is vector equation. Yeah. Here we can we have introduced these Christoffel symbols and covariant basis vectors. Now we can change the dummy indices. We can change the dummy indices to any other indices. Now here in the second part of the right hand side of the equation, we can see mu. Mu and k are dummy indices. These dummy indices can be interchanged. Now when we interchange the dummy indices, we will have mu to k, k to mu. Now, when we interchange these dummy indices, we can take epsilon k common. Then the terms in the bracket will be k. Now we have the term in the bracket which has two terms. You can see here the first term is actually the coordinate derivative. This is coordinate derivative, and second term represents the change of v is changed by coordinate basis vector. So this term is known as covariant derivative of contravariant vector. Vector, and this term is denoted by v k semicolon j. A semicolon is introduced here, or semicolon is involved. This derivative is sometimes called semicolon derivative of contravariant vector. So coordinate covariant derivative of contravariant vector is also called semicolon derivative. Now, when we write in symbol, the vector equation becomes epsilon k. We have this vector equation single vector equation. Here, this epsilon k is covariant basis vector. This is basis vector, or we can say tensor of first rank. This is a vector. This is also vector. We can say this is also a tensor of first rank. So Vkj must be a tensor. So we say this is a mixed tensor. Mixed tensor of rank second rank or rank 2. Rank 2. If we see the transformation equation of Vk, we cannot say this is a tensor. It does not have the property to be a tensor. But from the relation of quotient rule, quotient law, we can say this is a mixed tensor. Now, finally, let me express the covariant derivative of contravariant vector. Vk j equals to this first term coordinate derivative that depends on the coordinates of the system. Here it is written generalized coordinate, and this k j mu v mu, this is change of vector is caused by the change of basis vector. So this is about the covariant derivative of contravariant vector. Now let's go to the another title, that is covariant derivative of covariant vector. To discuss on these topics, we start from the transformation relations of the component of covariant vectors. Now, this is component of covariant vector, and its transformation equation is Vk. In case of generalized coordinate, what we can write here? Qk is generalized coordinate. Okay. Now, as before, we differentiate this relation with respect to Qj. Okay. So we have again a basis vector. This basis vector is here. We can see the basis vector is here. This contravariant basis vector. This is contravariant basis vector. Vector. It is denoted by epsilon k. We express this relation in terms of contravariant basis vector. We can express the whole equation in a single vector equation. So the single vector equation is okay. Here is a term that can be expressed in terms of Christoffel symbol of second kind, but this is not directly related to Christoffel symbol of second kind, as we have seen in previous case. So we can have some mathematical operation so that we could change this relation in terms of Christoffel symbol. Let's start. For this, we can start from here. This dot ej equal to ij. This is the obvious relation. Now we can differentiate this relation with respect to qm. Plus 0. So delta ij, when differentiated, it will be 0 because it has only two terms, 0 and 1. Now rearranging this equation, okay, here is this is here. Okay, this is j is down. And here also you can say this is not so. This is j here. Okay. Now we can change this relation in terms of Christoffel symbol. We have this relation in terms of Christoffel symbol. This is minus epsilon I. So when you change this relation in terms of Christoffel symbol, L mj epsilon L, epsilon L. Here this epsilon I dot epsilon j, epsilon L is delta IL. So we can write here minus L mj delta IL. So this delta IL has only two values, 0 and 1. 0 when I is not equal to L and 1 when I equal to J. So we can write this expression as, this expression I m j. Now, again, we can rearrange this equation. Here, this will go to the right side with some mathematical operation. This covariant basis vector will be contravariant basis vector when we move it to the right hand side, but some mathematical operation is required that students can do. So here, I think J. Now, the relation, we can say vector relation is here. Let's recall this vector relation. Okay. Here we see the relation. Here is del epsilon k by del qj. We would like to make this relation the same. So for this, what we can do, we can just replace the indices as I to k, m to j, and j to mu. When we replace the indices in this way, we'll have the same relation. So that we can replace the value of this in the vector equation. So here, when replace, the relation will become j mu. Here is, this is j. We have replaced this relation. So we can substitute this in the vector equation. When we substitute this in vector equation, we have minus yeah, we can substitute here and we'll have this relation. Now, here in the right hand side, second term we see mu and mu, they are dummy indices. K and K are also dummy indices. These dummy indices can be interchanged without altering the result. So, K, mu to K and K to mu. Now we can take common. Epsilon K, this contravariant basis vector can be taken common. When you take common, we will have the vector relation the term in the bracket is, this is the coordinate differentiation, coordinate derivative, and this is common. So this term, it has two terms, coordinate derivative and change of vector, a change of basis vector. This term is called covariant derivative of covariant vector. And it is denoted by V, K, there is K semicolon J. Now this is also called semicolon derivative. So if we express in symbol, then we have again we can see this is vector or tensor of first rank. This is also a vector or tensor. So this must be a tensor or mixed tensor of rank 2. Mixed tensor of rank 2. Here again we say this does not have the transformation equation is of tensor, so it does not has the quality to be a tensor if we consider a transformation equation. But as a result of these two equations, this relation, we can consider this is a tensor. Now final relation we can copy here, this V what we can say contravariant covariant derivative of covariant vector and covariant derivative of contravariant vector. We can write here this K J. This is covariant derivative of contravariant vector, and it is first term is Vk over Qj. This is coordinate differentiation that depends on the coordinates plus gamma K J mu V mu. This is another term. Similarly, V, this is covariant derivative of covariant vector. And here, again, first term, this is simple differentiation derivative. Sorry, here this is J. This is not K. Here J minus mu J K V mu. These are two derivatives, covariant derivative or semicolon derivative of covariant vector and contravariant vector. So we have seen here each of these derivatives have two terms, one coordinate derivative, another change of vector is caused by the change of basis vector. In next class, we'll discuss about the Christoffel symbols of first kind and second kind. This much today. Thank you.